Okay, here's another exam question on NMR, and it this time has a bit of carbon-13 NMR in it, so that's good. So cracking straight on with 8.1, give the skeletal formula. Okay, so skeletal formula is where you just draw lines for your covalent bonds and your carbons on the corner, and you don't include the hydrogens, as you'll remember. Okay, so the compound that's used as the standard is, of course, TMS, tetramethylsilane. While we're here, it's not what the question's asking you for, but while we're here, it's used because the hydrogens in tetramethylsilane are chock full of electrons, so there's a lot of shielding. Okay, so when we compare other compounds to it, right, then it's going to be a good bit of difference that allows the spectrum to be clear. Okay, so tetramethylsilane, you're going to have some silicon in the middle, and it's in group 4, you've got 4 bonds off it, and each end of these bonds is a CH3 group, but because it's a skeletal formula, we don't write anything else, and so that there is what you write for your 1 mark. Okay, so next part of the question, 8.2, we've got 4 isomers of this molecular formula here, with 2 oxygens in it, PQRNS, and looks like we're going to use a carbon-13 NMR spectrum, or several spectrums, right, to work out, to match the spectrums to the PQRNS. Looks like that's what we're going to do. Just before we do that, let's look at this and do our little trick on it. Remember, CnH2n plus 2, and if that's true, there's no double bonds. If it's not true, then there are double bonds. And here we've got 6, and 2n plus 2 would be 14, and we've got 12. So there is double bonds there. It could be a double bond between a carbon and oxygen. It could be a carbon-carbon double bond. We don't know yet, but at least we know that there's going to be a double bond involved. So in part of the question I didn't cut and paste, it said use these 3 spectrums to match PQRNS to those 3 spectrums, and also use the data sheet as well, which is here. So in order to match the molecule PQRNS to its spectra, then we're going to count environments and compare that to the number of peaks. So start with P. We've got 1 environment there. That's a different environment. That's a different environment again, and again, and again, and again. So each of those carbons are in a different environment. These CH2 groups, they're all in CH2s, these 3 here, they're all CH2s, but they're different distances away from the electronegative oxygen, so they're in different environments. So here we've got 6 environments. Okay, moving on to Q. Again, we've got 1 environment here. This CH3 is in a different environment, but that's in the same environment as this one. This is a CH2, so that's number 3. This is carbon attached to a double bond oxygen, so that's clearly 4. And this CH3 connected to a double bond is going to be 5. So we've got 5 environments for Q. Looking at R, start off with this one, that's clearly an environment. The CH3 group and this CH3 group and this CH3 group are all in the same environment. So that's 2. The CH2 group is going to be different though, so that's 3. This is different again, it's 4. So we've got 4 environments in this one. Okay, moving on to S, 1. So again, in the same way, but this is going to be 2, 2, and 2, and 3, and here is 4. So we've got 4 environments here for S as well. Now let's count some peaks. In the top spectrum we have 1, 2, 3, 4. In the middle one we have 1, 2, 3, 4. In the bottom one we have 1, 2, 3, 4, 5. Okay, so now we match. Okay, so just changing colour. Then we can say that P, because we don't have a spectrum of 6 peaks, we don't have any P. We have one spectrum with 5 peaks, so this bottom one must be Q. But we can't tell whether the top one is R or S yet. Okay, so let's have a look at the differences between R and S. The left-hand side of the molecules look pretty similar, so let's ignore that. In R, we've got this carbon here. We could see if we could find that carbon here on the table of chemical shifts, and then see if we can find a peak for that. But we don't find a carbon that matches that carbon in that the arrow is pointed to in R. This one is similar, but in our case we've got an R hanging off. Yes, it's not the same, right? So we don't have that carbon, I don't think, in our table. So let's move across to S and have a look at S. This carbon here. Okay, so that is a carbon in a methyl group that's attached to an ester link. Okay, so let's see if we can find that carbon. So looking at your table, look at this carbon here. It's attached to 3 hydrogens and a single bond to an oxygen, which is the same as our carbon here. Okay, so if we found a peak for our carbon in S between 50 and 90, that wasn't there for R, then that would be probably our answer. So looking at the top one, it's just 50 here, and so that is our peak that we're looking for. This peak here is just below 50, and so that tells me that this is S, and therefore this must be R. In an exam I'd move on now because I'm confident enough not to have to check it, but for learning processes we might just look at it in some more detail. So for interest's sake we can have a look at these 2 peaks here, this one and this one. They look pretty much the same, virtually 180, which is the carbon attached to a double bond in an ester or an acid. And in this case we've got our acid, and in this case we've got our ester. Alright, so there are peaks there that we can explain, and if we'd have started off with that, we wouldn't be able to differentiate them, but as I said, we're just learning here. Let's have a look at, let's change colour again and have a look at these 2 peaks. Alright, so these 2 peaks are carbon-carbon double bonds, and of course there's loads of carbon-carbon double bonds in R and S as well, and there's also a carbon-carbon double bond in between our CH2 molecule, in our CH2 part of the R molecule, which is slightly different to the other ones, but only a tiny amount different. So I would say that that peak there is this carbon here, because it's involved in carbon-carbon double bonds, very similar to the large peaks there, but in a slightly different environment, which gives it a slightly different chemical shift. And in S you see there's no CH2 between the carbons there. So that would suggest further that this is R. Okay, so we've got a little bit more evidence there. So there we go, let's move on. Okay, moving on to 8.3 quickly, because this is not that tricky. I've cut and pasted the question here plus the table from the data sheet. And so we've got 3 isomers with that molecular formula, and we've got their infrared spectrum for each one, and we've got to identify, okay, using the peaks and the wave numbers. Okay, 6 marks, so that means we're going to need to say 2 things per isomer. Okay, so let's start with isomer T. We can quickly recognize this peak here as an OH from an alcohol, 3230 to 3550, and just come down. Yeah, so that's the OH from the alcohol, ALC that's supposed to be. And this is another interesting peak here. Okay, so this is about 1700 and so, isn't it? All right, so this is going to be our carbonyl group here. So we've got a carbonyl group there. So there's one carbonyl group, functional group, and one hydroxyl group from an alcohol, not an acid, all right, in the isomer T. So it's not a carboxylic acid. So there's going to be 1 mark for saying this and another mark for saying this. So moving on, let's do isomer U next, shall we? So for isomer U, we have this peak here, which is also the OH group of an alcohol. Right, so let's write OH alcohol down. Let's not get confused about this peak here. It sort of looks like it could be the OH group of an acid, but it would have to be a bit broader like that to be the OH group of an acid. And what's more, we've only got 2 oxygens in the molecule, and we can't have the OH of an acid without also having a carbonyl group there as well. Okay, so we're going to ignore that. And also, just like I've drawn just there, we see we haven't got the carbonyl group. And so if we haven't got a carbonyl group, and we haven't got an OH of an acid, but we have got an OH of an alcohol, and in the molecular formula we've got 2 oxygens, we must have 2 of those. It is possible to have a cyclical ether, of course, but that would be a bit bizarre at A level. So let's stick with a diol instead. Okay, moving on to isomer V, and this is quite an interesting peak here, which it's quite broad, and it finishes about 3000, and does involve an oxygen as well. So we're looking at this one here, which is an OH group. All right, so let's say that's the hydroxyl group of an acid this time. Okay, so if we've got a hydroxyl group of an acid, we must have a look for the carbonyl group of the acid. And then, as before, we're going to find that at around 1700, which is going to be this peak here. All right, so this is our carbonyl group of an acid. Yeah, so our isomer V is a carboxylic acid with those 2 functional groups there. Okay, 6 marks, done. Okay, next part of the question is quite simple. We're going to get the integral numbers. As you can see from here, we've got decimal fractions, and we want whole numbers because we can't have part protons. Right? And we've switched now to proton NMR, and as we know, we're going to pick the smallest value, which is 0.6, and divide each one by 0.6. Right? So that's 1, that's 1, that's 1, that's 1.5, and that's 1.5 as well, and we still can't have 1.5, so we need to do a further step, doubling it up. So let's just go, that's going to double up to 2 and 2 and 2 and 3 and 3, and so there are our simplest ratio of the relative number of protons in compound X. Let's just check by counting our hydrogens. We've got 2, 4, 6 plus 6 is 12, and 8 plus 2, there's 12 there, so we're correct. Okay, moving on to 8.5. It says use table 3 and table B, and here they are. That's table 3 and that's table B from the data sheet. Alright, to answer this question. And as we do, let's just rewrite these numbers. This turned into a 2, didn't it? A 2, a 2, and this turned into a 3 and a 3. So we had that from before. And what we have to do is the part of the structure that occurs at shift equals 3.5, we have to do that part of the molecule, and the same for shift equals 2.2. So let's look at this part of the table here, the sigma 3.5. So from the integral value of 2, we can get that it's a CH2 group, 2 protons. And from the 3.5, we know that it's close to an oxygen, and let's just point it out here. Right, so it's going to be a CH2 group connected to an oxygen. So let's write that down, CH2 group connected to an oxygen, and we know also from the fact that it's a quartet that we're going to have it will have, so let's put a full stop and write it there. It will be attached to a carbon with 3 hydrogens, right? Because it's 4 take 1 is 3 from the reverse of the +1 rule. Good. So it's going to be oxygen, CH2, CH3. I think that's worth 3 marks, but there's only 2 marks for it. So let's have a look at the signal at shift equals 2.2. So we've got 3 protons from the integral value. All right, so it's going to be a CH3 group, and we've got a singlet. All right, so that means there's going to be no neighboring protons. And this is the bit of the table that we're going to refer to at 2.2. So we've got CH3 group attached to a carbon with no hydrogens attached to it. Instead, it is attached to C double bond of a carbonyl group. Okay, so let's just draw it out. There's our carbonyl group. There's our CH3 group. Okay, so last part of the question, 2 marks for putting the molecule together. We're reminded of the molecular formula, C6H12O2. So before we do it, let's just write down what we did do in question 8.5. We had oxygen connected to a CH2 group. Let's draw it like this. Connected to a CH3 group. that was for signal 3.5, and didn't we also work out the signal for 2.2, which was like this? We had a CH3 group connected to a carbonyl group, didn't we? So that's just a reminder of what we worked out in 8.5. Now what we've got to do is put them together with any other bits that we haven't thought about so far. And let's see, we've got C6, so we need 6 carbons, and we've only got 4 accounted for so far. And we need 12 hydrogens, so let's see, we've got 1, 2, 3, 4, 5, 6, 7, 8, so we need another 4 hydrogens, so we need plus, what did I say? I said plus 2 carbons, right, plus 4 hydrogens, and we've got both our oxygens. Okay, so this would suggest we need to add in somewhere 2 CH2 groups, like that. Okay, the other thing that I point out is that CH3 groups are usually the ends of molecules, aren't they? Alright, can't go any further. Alright, so we have to turn one of these round. Let's turn the red one round. Alright, so we'll draw our CH3 on the left this time, next to our CH2, next to our oxygen. Alright, and our green bit of the molecule is our other end, because CH2 groups are good in the middle. Alright, so we're going to leave our green for a little bit and put our 2 CH2 groups in, like that, and then we can just finish off with our green bit of the molecule. Now, before we go on to the next question, let's just check with balance. So 1, 2, 3, 4, 5, 6 carbons, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens, and 2 oxygens. So it looks like it's good.